Okay, welcome back. Let's continue our class. Okay, so I want us to revisit what we did last time so that we are familiar of what we are doing as we progress forward. That we begin with the rank 1 constraints. Of course, we had learned how to write algebraic circuits. So what we'll be doing now is just converting the algebraic circuits to rank 1 constraint systems. Now, for those who are not with us that time, algebraic circuits are just equations. And these are equations that we use in zero knowledge proofs. So, but those equations, the way we write them, has to be in a way that it can be converted to rank 1 constraints. Now, after we've learned about rank 1 constraint, that is now when we shall be looking at zero knowledge proofs, but they are not very much far apart. They are just related concepts. One leads to the other. Now, I've already stated that what we'll be doing is once we have the algebraic circuits, what we'll be doing now is just to transform them into rank 1 constraint systems. So therefore, we need to know what we mean by rank 1 constraint systems. Okay, some books would use this one, some books would use, okay, when you're writing this, some books would use this and others would use just the one, this one. So whichever thing you're reading, it means the same thing, rank 1 constraint systems. Now, what are they? What are these equations? When do we say that an equation is in this form? When do we say that an equation is the form of rank 1 constraint system? Now, an equation is in a rank 1 constraint if it has only one multiplication, but additions can be several. We can have several additions, but multiplication must only be one. That's why I've said an rank 1 constraint system represents an arithmetic circuit. Say arithmetic circuit is just an equation of this form. So if an equation is of this form, then we shall say that this is a rank 1 constant system. So you can see this equation has only one multiplication this side. And then you have the other side. But now we could have several additions. And that's why I've said that additions are unrestricted. So you do not need to have some number of additions. You can have as many as you can, but you ensure that multiplication is only one in your equation. So what we should be doing is, once you have an equation, we want to ensure that this equation has only one multiplication. That is our goal. Once we have that, once we achieve that, and then we have achieved, our equation is now in a rank 1 constraint format. Now, so I've noted here that once you have the equations in this format, and then they will align very well with what we had learned earlier about bilinear pairing, which we shall then be using in our snacks, the ZK snacks. So that means having an equation in this form is leading us to the zero knowledge proofs. once you have an equation in this form, then it will have led us to where we want to be. And so let us just move slowly towards the zero knowledge proofs and see how we arrive there. So we have what we call a witness, and we know that when you're talking about the zero knowledge proofs, we have the witness, we have the verifier, and we have the prover. Now we want to then know what is a witness as far as rank 1 constraint system is concerned. What is a witness? What do we call a witness? You're given an equation. Let me say we have this equation. C is equals to A times B. And I've ensured that there's only one multiplication on one side. Let me even say plus C. And we say that there's no limit on the number of additions you can have. You can have as many additions as you can, but multiplication should only be one. So you have this equation. This is the equation. Somebody claims to know what C is. Somebody claims to know what C is. So that means this person should give us witness. Should give us witness. So what do you mean by witness? If he claims to know what C is, this person is supposed to give us some A, give us B, give us C, give us D, and give us C without revealing the exact C. Without revealing the exact C. So it's just giving us some numbers. And those numbers, when we do the arithmetic on the right side, they give us the C the person has given us. And then he might also give us other numbers different from the ones he gave us earlier. And again, when we do our calculation on the right side, he should give us the C the person gave us. Now, these then are the witnesses. So in this case, our witness will be the value of A, the value of B, the value of C, the value of D, and the value of, let me see if I can mute Anthony. Okay, so in this case, the person has given, this person who claims to know what C is, this person should give us C, some A, some B, some C. Oh, there cannot be a C, two C's. Then we call this an E. We call this an E. So this person who claims to know what C is supposed to give us some C, give us A, B, E, D. Now, of course, he's not giving us the exact C, but what the person has given us is what we call a witness. I mean, it's not, these are not the only ones. These are not the only witnesses. So we shall now go, as we proceed, we need to know what our witness is. But I've just given you that what we know from is that then the witnesses should be the values of this. But I'm saying that these are not the only values this person is supposed to give us as a witness if he claims to know what C is. So then what should this person give us? Of course, he's be giving us A, B, C, D, but those are not the only things we'll be acquiring from him if he claims to know what C is. So I've said in an arithmetic circuit, a witness is an assignment of the values to all signals that satisfy the constraints. That is in an arithmetic circuit. So what I've just said, when we were given A times B plus E plus D, this is an arithmetic circuit. Now, so the witness, I'm saying, for an arithmetic circuit, the witness will be the values of A, B, C, D, E. What about in rank 1 constraint system? In rank 1 constraint system, I've said those are not the only witnesses. So in rank 1 constraint system, the witness is a vector. Is a vector, and this vector is a 1 by n vector. In other words, these are vector of one row and several columns, n columns. So several columns, but one row. So it's a 1 by n vector containing values of all input variables. So when we talk of input variables, we get meaning C, meaning A, B, E, and D in this case. Those are not the only values. We've said it must also include, okay, the input values and then the output, or the output in our case is C, and the inputs are this. So a witness is a one row vector that comprises of the input values A, B, E, D in our case. It also comprises the output value, which is C in our case, and then the other intermediate values. So these intermediate values come as a result of, supposing we had several multiplication, we want to ensure that we have only one multiplication. So in the process of ensuring that we have only one multiplication, where there were several multiplications, you come up with the other intermediate values. So those other intermediate values also make up part of the witness, a part of the witness. Now you're saying, one, you must know the inputs. This person must give us the inputs, give us the output, and apart from that, this person should give us intermediate values. And of course, there is also a one. There is also a one. So I've said, conventionally, the first element of the witness will always be a one. The first element of the witness will always be a one. That is conventional. That's how you write. That's how you write a witness. Now you'll see how a one coming as the first element of the witness is very important as we progress with our lesson today. I just want us to look at this. Now, so supposing we have this equation, supposing this is an arithmetic circuit. From this arithmetic circuit, you can see that what we have is Z equals to X times Y. So you can see that we have more than one multiplication on the right side. Of course, this is our output, but now the input here at the input side, we have more than one multiplication. And as we said, we must have only one multiplication. So to have one multiplication, we shall come up with an intermediate values that we talked about. So we can say, for instance, let X times X be V1. So if X times X is V1, then it means that Z then becomes V1 times Y. So this time we now have only one multiplication, and that was our target. Our target. Yes, somebody's talking. Okay. So our target was to have only one multiplication. This is one way. There are several ways you can do this, but the target is there must only be one multiplication at a time. At the end of it all, there must only be one multiplication. So one might want to do it that way. Another person might want to do it as, say, let X times Y be V1, so that Z becomes X times V1. So that finally you have only one multiplication in your final equation. Now, so I'll now stick to the first option as the one I've used in my example. The option where X times X becomes V1, and then Z now finally becomes V1 times Y. So what is our witness? What is our witness? We now have our equation in the form that we wanted it to be, the rank 1 constraint system. For us to have an equation, if you're given an arithmetic circuit, you want to have a rank 1 constraint system, and for you to have that, you have to ensure that you have only one multiplication. It doesn't matter the number of additions you have, but for multiplication, it must only be one. So where there are several multiplications you are trying to maneuver around, the way you've seen what you've done, there could be several. There could be several. Let me see. Supposing I have this. Supposing I have X, Y, Z, M, N, F. There could be several multiplications, but the target is you must have only one at the end of it. So you might want to combine these two, for instance, and call it a V1, so that you have X, XY is V1. You may also want to combine this and call it V2. You may want to combine VM and N and call it V2. So you may want now to say, that Z is V1 times V2 times F, but these are 3 multiplications. So you may want now maybe to say that this is V3. Want to say that V1, V2 is V3. So that Z now becomes V3 times F, V3 times. So finally, we have only one multiplication. Now, so this becomes an intermediate value. This is another intermediate value. And then this is another intermediate witness. Apart from, in addition to this, you see, these are part of a witness. These are part of a witness as Z. This X, Y, M, N, F, Z. We have the intermediate values that we formed along the way. As you are trying to come up with the only one multiplication, the other intermediate values you came up with, they form part of a witness. So you can see we came up with V2, came up with V3, V1, V, and so on. They form part of a witness. So example, and write a witness for this example. The example that we've just looked at, one that we have Z is X squared plus. What is our witness? Our witness would be, we say we begin with 1 always. We said this is 1 by n vector, 1 by n vector, meaning that there's 1 row and n columns. So we have 1, then we have Z, then we have X, then we have Y. So you can see I've just written 1 is always, conventionally, I said conventionally, 1 will always be the first element of the witness. Then we have the output. Then we have the inputs, the output, the inputs. Then after the inputs, you have the intermediate values. And in this case, we only had 1 intermediate value, V1. So this is our witness. This is our witness. Our witness is 1, Z. So what if somebody claimed to know what Z is? If somebody claimed to know what Z is, this person is supposed to prove to us that, of course, he knows by giving us a value of Z, not the exact, not the real value, any value of Z, and then give us an X, give us a Y, then give us an intermediate value. So for instance, this person, supposing this person can say, that Z is 36, can say Z is 36. And so when he says Z is 36, then he should give us X. Maybe he can tell us that X is 3 and tell us that Y is 4 and tell us that V1 is 9. So that now our witness becomes, in this case, our witness will be 1, that's 6, 3, 4, then 9. So the person claimed to know Z. So we ask this person to show he knows what Z is. He's not giving us the exact value of Z, but he's giving us this. Once he gives us this, it's us now to verify that what he has given us exactly shows that he knows Z. So we just come and try. Z is that 6. We want to see whether it's true that 3 times 3, then times 4 will give us that 6. Okay, that one passes that test. We also want to see whether V1 has given us V1 as 9. We want to see whether V1 will be 3 times 3. So this person has passed that test. So we may again ask him to show us, to give us another witness. May ask this person to give us another witness, and again, this person gives us another witness. And we go through and show that, of course, this person knows what Z is. But of course, we'll not be doing it manually like this. Not be doing it manually. Once this person gives us the witness, we'll be writing Rust code that will then be assisting us to verify. Now, so that is now what we call, if you know how to write that, if you know how to write that program, it means that you can now write zero knowledge proofs. Because that is what we then be writing. Okay, just before we progress, of course, we've seen what a witness is here, what a valid witness. Let me just go through what I had written. What I had written, I had said a valid witness means not only the value of X and Y and Z, because we had been given Z is X squared times Y. And now a valid, when we say this witness is valid, it doesn't mean that for it to be valid, it's not that you are only to be given X, Y, and Z. But you must also be given intermediate values, which we've seen in our case B1. This person must give us B1. And then the valid witness must have a 1 as the first element. So this is now what we call a witness. Now, so how many columns do we have? And how many rows do we have? Now, the number of columns, I'll begin by answering the number of columns. The number of columns, I can see 1, 2, 3, 4, and then 5. Okay, now they depend on, the number of columns will depend on how many inputs were there and the output, and then how many intermediate values were there. So if the intermediate values are 2, you should all see all of them 2. You should see the 2 here. And if the inputs were more than 2, you should see all of them. So the number of columns will depend on that. It will depend on how many inputs were there, how many intermediate values were there, and then the 1. Now, okay, this is just an explanation that I had already given. So supposing this person, okay, this one I used different values, but of course I said every time this person gives you values, you ask for other values. In fact, this should be should provide several times so that you are sure that this person indeed knows what he's talking about. So for this example, again, this person may, if you were to ask for him to give us other values, another witness, he might maybe this time give us Z to be 18, give us X to be 3, give us Y to be that, And then after that, we just want to verify that what he has given us is correct. So we want to verify that so you must also give us V1. So if it gives us V1 to be 9, we just want to verify that 9 is x squared, which is 3 times 3. Then after that, he has given us Z. So again, we verify whether V1 times Y gives us 18, and V1 has been given us 9, and we verify by multiply by 2, we want to see whether it's 18. So this again becomes a valid witness. Apart from the one we had looked at, this is another valid witness. Now, so I'm looking at another example. Looking at this other example, and want to write, this is an arithmetic circuit. This is an arithmetic circuit. We want to convert this into a rank 1 constraint system. Now, lucky enough, we only have one multiplication, so this is very easy for us. So if you are to be asked about a witness, for this, we do not have an intermediate value because we already have only one multiplication. There is no intermediate value, and therefore our witness will be 1, then Z, then X, then Y. So this will be our witness. So if we ask this guy who claims to know what Z is, to show us that he knows what Z is, this person will come up with the value of Z, should give us a value of X, should give us a value of Y. So for instance, this person has claimed that Z is 4223, and then he's claiming that X is 41, and that Y is 103, and that gives us Z. So if we ask him to show that he knows what Z is, he decided to give us this. You ask him another time, he'll give another value. He'll give you, for instance, he can give you 2 to be X, then give you 13 to be Y, and then give you Z to be 26. You're asking for another value. So for this one, it's very easy. For this one is very easy. So, but I want to use this to write a program that will be verifying that the witness given to us is correct. So that will begin from here, then generalize to other forms where it's somehow complicated. We'll begin with the easy ones and then build on the easy ones going forward. Now, so we want to write a program. So what do we require? What do we require? So first of all, you have the witness, so that is okay. And of course, the witness, we can see it's valid because the first entry is 1. You can see that when you compute this, they give us that. But of course, we are not going to do that manually. We'll be trying to use a program. But before we write a program, let's see how it looks like. We had Z is equals to X, Y. Now, so Z here is the output, which we call the result. And then on the other side of the inputs, we have the one that is on the left-hand side. The one that is on the left-hand side, then we have the one on the right-hand side. So when we talk of the left-hand side and the right-hand side, just referring to the inputs, not the result, not the output. You're referring to the inputs. So among the inputs, we have the input on the left side. Of course, you remember we have to first of all write this equation in a form that we only have one multiplication on one side, only one multiplication on one side. Once that is done, we identify the element on the left side and the element on the right side of that multiplication. Now, that is, we are now beginning to see how we'll be writing a Rust program. But that, first of all, the equation must be rank 1 constraint system format. And then after that, identify the output, then identify the left-hand side, and identify the right-hand side, just like we've done here. And then after that, we formulate valid rank 1. So how do you formulate that? Okay. We had already said that. Want to ensure that we have only one multiplication. Now, so this is a matrix. This is a matrix of the output, the matrix on the left-hand side, the matrix on the right-hand side, and this is the witness. This is the witness, and this A is the witness. So what we are saying is, once your equation is in rank 1 constraint format, identify the output, and I'll be showing you how to come up with these matrices. I'll be showing you how to come up with these matrices. Now, so you have, finally, you have something like V1 and then Y. Finally, this is what you have. Originally, what we had was X square Y. This is what we had originally. No, not this one. We are looking at a different equation. So this is what we had originally. Originally, it was the left side. Oh, this one does not have this. So I was referring. So that this is what we have. This is what we have. So the equation is already in rank 1 constraint system. The one we had, the example we're looking at. So this is the output. But now, what was our witness? Our witness was 1, Z, X, then Y. So now I want to come up with the matrix representing the output. So the matrix representing the output just come is this matrix, but now the only thing that we change is where there is Z, because Z is our output. Since Z is our output here, you change what Z is. Where there is Z, you make it 1. So where there is Z will be 1, and the rest you convert them to zeros. So this is the matrix representing the output. This is the matrix representing the output. So what I've just done, you have the witness. Once you have the witness, your work is almost done. You only need to convert. If you're writing the matrix O, you know that O is output. Your output is Z. So you go to the witness, Z, make it 1, and the rest make them 0. Now come to the left matrix L. Matrix L will again be the witness, but now L is the left-hand side. The left-hand side of this equation, is X. The left-hand side of this equation is X. Remember that Z is output, so we are only considering these two. So the left-hand side is X. So you make X to be 1, and the rest make them zeros. So this is our matrix L. Then what about our matrix R? R is the right-hand side. And again, our right-hand side of this equation is Y. So you make Y to be 1. and the rest make them zeros. So this is our matrix R. This is our matrix L, and this is our matrix O. And then we have the witness. But in our case, the witness, this person had given us Z to be 4223. And he had given Z to be, was it 41? I think 41. Let's just go back and see what X was. So this person has given us some witness. Of course, the witness is just this. This is the witness. So what it means is we have said that O was 0, 1, 0, 0, which of course we can write it this way. And then this is our A is 1, 42, 23, 41, 103. You can always write it as a column vector. And then we have L. L was Y. Okay, L, this one, we made this one 1. X, we made X 1, and the rest was zeros. And then again, our witness 1, 42, 23, 41, and then 103. Then multiplied by our Y, our R, we made Y to be 1, so the rest will be zeros. The rest will be zeros, but Y is 1. Then again, multiplied by the witness 1, 42, 23, 41, and then 103. So what you do, you see, this equation is, it means the witness is correct because you can just try to multiply. You can try to multiply. You know, we always multiply. When multiplying matrices, we multiply a row and a column. So this row and this column, as you add, 0 times 0, 1 will be 0. 1 times that will be 43, 42, 23. And then 0 times this will be 0. 0 times this will be 0. So the left-hand side has given us 42, 23. What about the right-hand side? The right-hand side, 0 times that will be 0. 0 times that will be 0. Then 1 times 41 will be 41. And then 0 times 103 will be 0. Then multiply by 0 times 0 will be 0. 0 times that will be 0. 0 times this will be 0. Then 1 times that will be 103. So you can see that the right-hand side is giving us the left-hand side. It means the witness given to us is correct. So what we'll be doing then is, once the person gives us a witness, we come up with these matrices and then write the Rust code that will be verifying by just doing what we've done, multiplying O by A, which is our witness, and equate that to L times A multiplied by R times A. So that is what we then be writing. And so that Rust code will then be verifying to us. And that Rust code can always be generating other values. Every time you want different witness, it gives you a different witness. So you can make it to randomly generate the witness for you. Because if it's you that wants to, they're asking you to give a witness, you just randomly generate and give the witness, randomly generate and give the witness. And so the person now that wants you to prove would now be verifying every witness you give him, verifies that it's correct, is valid. Now, so I've already explained what this means. I've already explained that L is the left-hand side. Of course, it's a matrix. And R is the matrix on the right-hand side. O is the one on that the output. And A is a witness. So what follows here, I was just explaining how to come up with the left-hand side matrix. So all of this is just explanation on how to come up with that matrix, and I've already shown you how to come up with that. In fact, I've just said, if you're given a witness, and you want to form L means if you have the equation as Z is XY, you're checking on this side, what is on the left? L stands for the left. So what is on the left, you make it 1, and the rest make them 0. So in our case, what's on the left here is X. So where there is X, you put a 1. And the rest, put zeros. So that is how you form our left-hand side matrix. What about our right-hand side matrix? Our right-hand side matrix, again, on this equation, the one on the right-hand side is Y. So considering our witness, make Y1. Make Y1, and the rest zeros. And then O is the output. Our output is Z. Again, considering our witness, make Z 1 and the rest be zeros. So this becomes our output. So from here, you can now go straight away to Rust code. And what you are writing in your Rust code is what is O. You're giving it O, you're giving it L, you're giving it R, you're giving it A. And then it will tell you if that witness is correct, if it's valid or not. Now, so this one I've already done. I was just verifying. And of course, we are not saying that we'll not be verifying manually. We'll be using Rust code. So you just verify. You just giving your Rust code your output O. Then give it A. It will do this for you. Give it L, then give it R. It will do this for you. And if it finds that the right-hand side equals the left-hand side, it will tell you that the witness given is valid. And it finds that they're not equal, it will tell you that the witness given is invalid. Now, so the Rust code that then I'm referring to is here. This is the Rust code I'm referring to. You can see it's not a very long Rust code. It's a very short one. Because I'm dealing with arrays, I then use ND array. Of course, then they'll be, since it's here, I'll then be using cargo toml will also be having this. And then I have the main function, just defining our O as this matrix, our L as this matrix, and R as this matrix. And then the witness, the guy has given us this witness. I put it there. So once I put it there, I'm telling this Rust code that now compute for me the left and the right sides of the equation. Remember the equation was Z is XY. So I wanted to compute for me the left side and the right side. But of course, it's not using this. It's using the left side is O times A, and the right side is L times A multiplied by R times A. So this is what Rust code is now doing for us. So it finds for me the left side. Dot here means multiplication. So O times A, and then the right side, L times A multiplied by R times A. And then after I'm telling it, after you've found the left side and found the right side, now check if the left side and the right side are equal. Now check if they're equal. And if they're equal, then it means that the rank 1 constraint system has been verified. But if it's not, then that means there's an inequality. It means they're not, if they're not equal, it's supposed to tell me that these two are not equal. So that is what, but now, the example we've looked at is where we have an equation in rank 1 constraint system format. And so that means going forward now we'll be looking at where they are not in that format. We have several multiplications and want to reduce them to 1. Of course, that is always our target. The target is that if you have several multiplications, you want to convert them to, want to play around with them until you have only one multiplication on one side. Now, so this is the code. You can see the output matrix. The left and for the right is here. Then our witness has been input. And then you are telling it that find the left side. That is multiply the output times A. And then the right side, let the right side be this. And so if this is the right side and this is the left side, check if the left side and the right side are equal. So let's just see, let's see if they're equal. Let's see what it tells us. Now, so this tells us that the left side and the right side are correct. That means that rank 1 constraint system has been verified successfully. So that means if this guy had given us a wrong witness, one of the values, let me change this 41 to 42. If he had given us one value that is wrong, this code is supposed to identify that it's wrong. So if he gives us one of the values that is wrong, this is what it gives us. The process did not exit successfully. That means one of the values is not correct. Now, supposing this was correct, supposing the 41 is correct, but now the right matrix here is not correctly written. Supposing the 1 is placed where it's not supposed to be. Again, this is supposed to know that it's then it's not correct. So again, that will give us an error. Okay, let's try a slightly complicated one, slightly. Of course, we just said we begin with the one that is the one that we've just done, which is easier. Then from there, we try to complicate it as we move along. So let's look at this one. Now, this one we have several multiplications, and of course, we've said our target is always to ensure that we have only one multiplication. So we have our output, R is X, Y, Z, U. There are several ways. One may want to say that let V1 be XY and let V2 be ZU. So that then finally R becomes V1 times V2. Now we've already achieved our one multiplication because we say that rank one constant system must have one multiplication. We've achieved that. That is one way. One may want to look at it that way. Another person may want to even combine even maybe X and Z, and combine that. Call this one V1, call this one V2, and then arrive at that. There's no problem. Another person may want even to say that let XY be V1, so that you have R is V1 multiplied by ZU, and then call V1Z as V2. So call V2 as V1. Let me write it here. So I'm saying another person, apart from looking at it this way, another person may want to maybe say, let XY be V1. XY. And then after that, so what would we then be having? We'll be having R as V1 ZU. So this person wants to call this to be V2, so that V1 Z would then be called V2. So if that happens, then we'll be having R as V2 U. This person would now have achieved rank one constraint system. The equation is now in that format that the person wanted, that you have only one multiplication at a time. You can see you have only one multiplication. The original equation now has only one multiplication. That is what we wanted to achieve. So it doesn't matter which route you take, but the final thing is that the original equation you began with should have only one multiplication. Now, let's take the first case. Our target is to come up with a witness. Our target is to come up with a witness. And then after coming up with a witness, our other target, therefore, is to come up with the output matrix, the left matrix and the right matrix. Then after that, proceed and write Rust code for that. So this is our format that I want us to pick. Of course, I've said it's not the only one. It's not the only option. You could have several options. But of course, the end result will be one. The end result will be the same. Now, if you have this, what would be our witness therefore? If you have this witness, we say we begin by writing 1, then write the output, then write the inputs, X, Y, Z, U. I'm just writing them in the order in which they are appearing. X, Y, Z, U. I've just written them in that order. 1, then output. Oh, output is R. Output is R. In this case, let me just write the correct output so that we do not have Z repeating itself. In this case, our output is R. And then X, Y, Z, U. And then after that, let me write the first intermediate value, then the second intermediate value. This is our witness. So if anybody claims to know what R is, then this person, without revealing the exact R, should give us an R, give us an X, give us a Y, give us a Z, U, V1, and V2. That will be the witness, nothing else. Nothing else. If this person claims to know what R is, this is what we expect that person to give us. Give us a 1. A 1, of course, would be obvious. But now we expect an R, an X, a Y, Z, U, V1, and V2. Then from there, we would go straight away to write the Rust code. And that Rust code will be giving it the matrices. I want to form our matrices from here. I want to form our matrices. Now, the earlier matrix we looked at, the equation we had been given was this. That I'm just referring to the first example. And this equation was already in the format we wanted it. So when we came to writing our matrices, we only had one row. When we came to writing our L matrix, O matrix, and R matrix, we only had one row because we had only one equation. In the present case, we have 3 equations. In the present case, we have 3 equations. These 3 equations. And therefore, our matrices L, R, and O would have 3 rows. Would have 3 rows. So the number of rows of these matrices would depend on how many equations do you have. So how many equations have you formed from the original one? Because we were trying to come up with the intermediate values so that finally we have the final equation as a product with only one product, only one multiplication. So in this process, how many equations did you form? So those equations would now tell us the number of rows you would then have. But the number of columns are still dictated by your witness. Your witness has how many columns? 1, 2, 3, 4, 5, 6, 7, 8. These are 8. So the witness has 8 elements, and therefore these matrices would have 8 columns. But the number of rows are depending on the number of equations you formed along the way. Good. Now, let's form those matrices. Let me begin with the left matrix, L. We've already known how many rows and columns we would have. 3 rows and 8 columns. Let's begin the first row. The first row is this. From here, we are forming the left matrix. Our left element is X. Our left element is X. And so where there is X here, make it a 1. So what we have therefore is 0, 0, x is a 1, and the rest again will be zeros. 1, 2, 3, 4. 1, 2, 3, 4. That's the first row. That's the first row of the matrix L, a matrix L. Let's just confirm that we have 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. Let's proceed to the second row. The second row, and let's remember that we are dealing with the left element. The left element is Z. So Z would this time become 1. This is Z here, become 1. So the rest will be zeros. 1, 2, 3, 4 zeros. 1, 2, 3, 4 zeros. Then Z. Then 1, 2, 3 zeros. And then finally, the third row, our left element is V1. So V1 this time becomes 1. The rest will be zeros. So the rest will be zeros. V1 becomes a 1, and the rest will be zeros. This is our matrix L. This is our matrix L. So that is how you form these matrices. And once you form these matrices, it becomes very easy to write the Rust code that would then verify any witness the guy gives to you. You can always verify that this witness is valid. Okay, let's write our matrix R. We remember that this matrix again will have 3 rows and 8 columns. Let's begin the first row. The right side of the first row is Y. Let's recall what our witness was. Our witness was, I don't know whether I recall, it was Z. And then it was, 1 Z, then X, Y, Z, U, V1, and V2. 1, 2, 3, 4, 5, 6, 7, 8. So the first row has a Y on the right side. So Y becomes 1. Y becomes 1, and the rest will be zeros. 1, 2, 3 zeros. Then Y, 1, 2, 3, 4 zeros. Let's go to the second row. U is on the right side. U is on the right side. So U becomes 1. U becomes 1. The rest are zeros. 7 zeros. Then finally, the third row, on the right side, you have V2. V2. So V2 becomes 1. The rest will be zeros. That is our L. What about O? Our output. O is our output. We go row per row. The first row, our output is V1. So V1 becomes 1, and the rest will be zeros. How many are they? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then with this one. What about the second row? Our output is V2. So V2 is 1. The rest are zeros. And then lastly, our third row, R is 1. Let me see, 1, 2, 3, 4, 5, 6, 7, 8. Okay. I wrote Z instead of R. I wrote Z instead of R. So it's R. R becomes 1, and the rest will be zeros. So these are all. So we have our L, we have our R, then we have our O. From there, we go straight to writing the Rust code. And so the Rust code, we are giving it what L is, as we did in the previous one. We're giving it what R is. We're giving it what O is. And when this guy gives us his witness, we're giving it the witness. Then after giving it R, O, L, and the witness, we are telling it that we find OA, because he has given us a witness. The witness is the A. We are telling it find OA. We are telling it find A, L, A. Then we are telling it find RA. Then after finding RA, we are telling it that the product of these two is the right-hand side, and this is the left-hand side. Confirm if the right-hand side equals the left-hand side. That's what we're just telling it. And if it confirms, then it means that the witness that has been given to us is correct. And if it doesn't, then it says that that witness is not correct. Now, so the only thing coming up with these matrices is very easy. The only thing is coming up with an constraints in rank 1 format, converting those arithmetic circuits, converting the arithmetic circuits to rank 1 format, rank 1 constraint system format. But of course, you've seen our target is not even easy to convert that. Our target is always, once you have that, ensure that you have only one multiplication on one side. Ensure that you have only one multiplication. So all these are just explanations of what I've already said. Ensure there's a 1 before this R. Ensure there's a 1 before that R, and so on. All of these are just explanations. Then this is the explanation of how to come up with the left matrix. Of course, this is a long way of doing it, but I've already shown you the shortcut of coming up with this left matrix. I've already shown you, but these are the explanations. In fact, let me now show you, so that when you're reading these notes, you must know what I wrote. I've done, I've tried to, you see that what we are given was R is given, R was X, Y, Z, U. So I've just said let B1 be this, and I'm telling you that of this will be on the left side, because we have the left side and the right side. And let B2 be this, and of course this will be on the left side, and then let R finally be V1 by V2, and of course again this will be on the left side. So the left side, what we have on the left side is X, Y, Z, and V1. But now you're going row by row. Every equation stands for a row. Every equation stands for rows. For instance, when you're considering row 1, x is the one on the left side. And that is why what I was explaining here. And I made it red so that you can see what I'm referring to. I've said in the first row, when you're getting L, in the first row, the equation involves this. This is a first equation, meaning that x is the only element on the left side. So this is the element we shall be making 1. When you have that, when you have the witness, where there is x, you put a 1. And the rest, you make them zeros. And that forms the first row, and that's what I was doing here. That's what I was doing here. So where there is x, I'll just put a 1, and the rest are zeros. Then I come to the second equation. The second equation, again, I identify what the left side of that equation is. And then that is what I was explaining here. So these are just long explanations. And then I'm saying that the second equation, z is on the one on the left. So where there is z, I'll be writing a 1. And that's what you're seeing. So I write the whole witness here, the entire witness, but z goes to 1. The rest, I make them zeros. Then I proceed to the third equation and do the same thing. The one on the left side is v. So all these explanations is what I've already explained. So it's not new. So again, I colored v1, meaning that is the one on the left side. So finally, therefore, your left matrix becomes that. Using the same, okay, I was showing there's an alternative for doing that, but the alternative is not easier compared to the one I've already explained. The alternative is not easier. But it's just the same logic, it's just the same logic. Finally, you'll arrive at L. Then now find R. Again, I'm explaining just, I come with this matrix, I identify the right side, the first row, the right side in the second row, and so on. And so that is what finally you arrive at this. Now let's now write the Rust code. The same thing we did earlier. The same thing we did earlier. Okay, this one, I put here rank, no, array A1 and array A2, and I discovered that when I was dealing with A1 and A2, I was not, it was giving me errors, so I deleted that. I put some imports and they were not giving me the results that I required. Now, so for this, I've added something small here, which was not in the first one. But of course, you can just copy this and put in the earlier one also. This one is just to generate for me witnesses. So I added this one just to be generating for me witnesses. So that I was looking at examples of witnesses that. So I asked it to generate for me witnesses between 1 and 100. So between 1 and 99, 191 included. You can increase this, but then we know witnesses are only 7. Now only 7. Not giving you R, it's giving you X, Y, Z, U. Then it gives you V1, it gives you V2. 1 is obvious. So this is what it will be giving you. So that is what I asked it, generate generate random values. So it will be giving me witnesses randomly. That is, if you claim to know what R is, then you need to have this part that will be generating for you the random values. But now, this is our left matrix. We just put it here. Our left matrix, our right matrix, and then our output matrix. Then ask it, okay, I asked it to generate X, generate Y, generate Z, generate U. Can even add it, generate R. Can ask it to generate it. Generate random value for R. So it will just be doing that. Then print those generated values. Print X, print Y, print Z, U, and so on. So you can add the R, and again, it will be generating that for you. Now, but this is not part of that. This one, I just wanted to give me random values so that I can use them for examples. Remember, this part was not in the first code. You can add it in the first code also if you wanted to generate values up to this part. It was not there. Now, so after you've input your R, L, and O, and then the witness, supposing this guy has given you a witness, let R, so this one is X multiplied by Y. And then Z. Okay, so what was this? What we had been given was, what was it? R was what? X, Y, Z, U. I think that's what it was. But then we came up with some intermediate values. So you're also defining them. Also defining what your intermediate values are. Your witness, you're defining the witness. So for this case, remember that I did not have any witness with me. So in fact, I wanted the code to just generate for me the witness. I wanted to generate the witness for me. So it will be doing that. So the witness will be in this form. So itself will generate for me the witness. And after generating the witness, multiply the left side. No, let the left side L. The L that we put there be L times that witness it has generated. Then let the right side be R times that witness that it has generated. Then let the output side be output times that witness it has generated. So this time I've asked it to just generate the witness for me. But you can still want to write the way we had written the first one. That is supposing somebody had given you a witness and you want to verify if that witness is correct. Now, so after it has done this, I'm telling it, let the product of these two, the left result and the right result, let it be called element-wise product. Let that be called element-wise product. Or if you can give it another name, there's no problem. Just what I want is LA times RA. I give it a name. And after giving it a name, I just wanted to tell the code to tell me if this side equals to OA. And what did I call OA? I call it the output result. I call it the output result. Let the output result let the output result be O times A. Let the output. So I now want it to tell me whether the output result equals the element-wise product. That's what I want it to tell me. Now, if it's correct, if they are equal, then it must tell me that verification is successful. But if it's not equal, then it must tell me that they are not, there's an error. I had not opened this Rust code. I want to see what I call it. I call it algebraic circuit verification. Let me just find it. Algebraic circuit verification. Yes, I've found it. I want to open it and then just share it. Whether you see how it randomly generates the witnesses for you. Okay. So this is the code. Let me check first of all and see whether what we have in cargo tomil. And this is what we have. And then this part I've said it will assist us to generate values randomly. And of course, what you want generated, you have to tell it what you want to generate. So as you generate this, I said you can add there R, you can add R there, and then ask it to print the generated values. Then you are just telling that R should be given by X multiplied by Y multiplied by Z, then multiplied by U. So this is just one equation that we had given. We've been given that R is X, Y, Z, U. And that is what I've just written here. That is what R is. So once it generates the X, Y, Z, and U, it's able to know what R is. And then you're telling it, we have intermediate values, V1 and V2. And then you're telling it how to get those intermediate values. Of course, if you wanted to generate the intermediate values, again, you can ask it to do that, to be generating that. But now, what is important to us is that after it has generated X, Y, and Z and U, and then the intermediate values, it's supposed to tell us what A is. It's supposed to tell us what A is. That is our witness. And we are telling it that the A will be A, there will be 1, R, X, Y, Z, U, V1, and V2. So you're telling it generates X, Y, Z, and U. And then we are telling it, after you've generated those ones, this is how you get R. And after getting R, we have the intermediate values. This is how you get them. Then after getting those intermediate values, now this is our witness. It gives us that. Then you are telling us, you're telling it that the left matrix, followed by A, shall be called left result. Then the right matrix, followed by A, shall be called the right result. And then the output times A shall be called output result. But now we want this product, the left result times the right result, to equal the output result. So we must give the left result, this product of the left result and the right result, one name. We must give it one name. And so I've called it element-wise product, element-wise product, which I'm taking as the left result times the right result. Now, I want it to tell me whether the element-wise result equals the output result. I want it to tell me whether it equals that, so that we can now say that verification has been successful. Let's just run this. Let's run this and see what it says. It has generated X as 11, Y as 16, Z as 99, U as 3. Then it's telling us that the equation holds. Telling us the equation holds. So it's now upon you to check and see whether what V1 is by multiplying X by Y, and check what V2 is. And then you want to check whether V1 times V2 gives you Z. No, gives you R. And of course, if you ask this guy to give you other values, this guy will be able to give you other different values, because he's trying to hide R, so he cannot give you the exact values. So every time you ask for values, it's generating different values every time. So again, this time it has given us X as 15, Y as 80, Z as 18, and U as 90. You ask for another value, and again, it gives you other values, because it's trying to hide exact values. You can never know what the exact values are, because it's just randomly generating those values. And it's upon you to now verify that they are correct. If you can verify they are correct, then you should be convinced. You should be convinced that this guy knows what R is. You should be convinced that this guy knows what R is. Without knowing what R is, you'll never get to know what it is, because the guy will just be generating values randomly. So that is that code, and I've explained how the working of the Rust code, how it works under this. I've even explained why the dependencies. Oh, initially I had put these dependencies RA1 and RA2, and then they did not work. RA1, okay, RA1 and RA2, it was running, but with the warnings, because it was not using RA1 and RA2 in the calculations. It was not, so I had to delete, and you saw. So, and I forgot to delete from the notes. From the notes here. You know what U128 is? Those are the bits, and so on. Okay, so that is what I wanted to cover today. Of course, today we just looked at one complicated equation. Now, I want to next time complicate it even more, but our target is always to write rank 1 constraint system. Whichever equation we are given, however complicated it is, our target is to ensure that we have only one multiplication on one side, irrespective of the number of additions. Now, so far, we've not had an addition or subtraction in any of our equations, but going forward, we'll now want to bring in addition and subtraction, and see how then we convert such an equation to rank 1 system. So that is what we'll then be looking at. Thank you. Okay, I want us to stop there. Hilda, any question?
No, I don't have any questions. Thank you for today's session.
Okay. Joan and Nelly.
Oh, this session, I love it.
Thank you for today's session. I really learned a lot.
It's okay, it's okay. Okay, so let's end it at that. Hilda, you are the one, you're the host?
No, you're the host. I'm the co-host.
Okay, okay, okay. So I'll end the lesson for all of us.